This video is another walkthrough of a lab activity, this time lab 2, so you are not required to watch it. But if you get stuck at any point while you're working on the lab, you can open up the video and find where I work on the same problem and see how I got past that sticking point. So our first topic is recursion in Racket, and recursion is really central to functional programming languages like Racket. And our initial example is a recursive function to compute a factorial. So we're defining a function called factorial. And we make a function with a lambda expression. Factorial takes one argument n. And then for a recursive function, we need both a base case and a recursive case. I'll do this a little differently from the PDF. I'll use an if statement. And so if n is equal to 0, the factorial of 0 is 1. And otherwise, we want to recursively call factorial. On n minus 1. And then that result that we get for factorial of n minus 1 needs to be multiplied by n to give us the factorial of n. So if we run our definitions, then we can compute factorial of 3, 5, or 10. The version in the PDF has the additional advantages of checking that the input is an integer and is non-negative, since factorial is only defined for the natural numbers. And so now our task is to define a double factorial function. And again, this will be a lambda that operates on one argument. And since double factorial is only defined on odd numbers, we want to add to our condition that it's a natural number that the input needs to be an odd natural number. So this time let's include that error checking and also add a check for the number being odd. So we'll have a cond statement, and we still want it to be an integer and non-negative, but we also want it to be odd. So we want that the modulo on n and 2 gives us 1. And let's verify that that does what we want it to. Modulo 5, 2 is equal to 1. And if we did 6, we would get false. Good. And let's also verify that the and of 3 things does what we want. And of true, true, true. That is a valid operation in Racket. So now, in this case, we want an error and must be an odd natural number. And now we have a couple more conditions. Again, we can have a base case of n equal to 0. And in that case, we'll return 1. And then we'll have an else, which is the recursive case. So here we want to multiply n by the double factorial evaluated on n minus 2. So if n, for example, were 7, then we would compute double factorial on 5, and then multiply that result by 7 to get the double factorial of 7. So we'll multiply n by double factorial evaluated on n minus 2. Let's make sure our parentheses all match. Looks good. We need to close out our cond statement. And now we can run our definitions pane. And if we compute double factorial on 7, we should get 3 times 5 times 7. Uh-oh, something went wrong. I misparenthesized here so that my and was only applying to the first two. So I want to delete that paren and add one over here. And now if we run double factorial on 7, I haven't figured out this error yet, but looking back at my code, I do see another error, which is that we're never going to get 0 when we're subtracting 2 at a time from odd numbers. So our base case needs to check that when n equals 1, we need to return 1. Since that worked, we conclude that actually the error wasn't with the mod 2, the error was with the greater than or equal to 0. And when we got to -1, we were getting that it's not greater than or equal to 0, and that error was propagating all the way out. So now we get 3 times 5 times 7 is 105. That looks right. So now we're thinking a bit about data structures in Racket, in particular the built-in list data structure, which under the hood is a linked list. And since Racket is a dialect of Lisp, and the Lisp family of languages are all about list processing, lists are a really fundamental data structure for doing anything in Racket. So there are a bunch of ways we can create lists. So the single quote gives us a list literal. We can also use the list operator to get the same thing. You can also refer to the empty list in various ways. And we can construct lists using the cons operator. So we can cons 1 onto the list 0, 2. And that will put the element 1 onto the front of this list. And that's an efficient operation because these are linked lists. Under the hood, it's creating a node for 1 and making that node point to the node for what used to be the first element of the list. And now 1 becomes the first element. And so also because it's a linked list, getting the first element is an easy operation that you will see a lot. So we can do first on some list. And that will give us the first element of that list. And then the complement to first is the rest function, which gives us the list that remains when we take the first element off. There are lots of built-in functions that operate on lists, things like reverse or append. First, rest, and cons are the fundamental list operations. They let us put things onto and take things off of linked lists. And so we can use those functions as the basis for doing anything we want to with lists, and all of the other built-in list functions are just for convenience. So now we're defining a function that operates on a list. And this is a lambda that takes one argument, and we call that argument LST. It would be a bad idea to call it LIST because that is the name of the built-in function for creating lists. And the objective of this function is to increment every element of the list. And we can do this by, at each step, incrementing the first element of the list, then calling our function recursively on the rest of the list, and then using cons to construct a list out of those two results. So the function empty ? Checks if a list is empty. And if it is, we can return the empty list. We could also have just returned to LST. And otherwise, we want to do our recursive thing, which is that we will construct a list out of two things, one of which is adding 1 to the first element of the list. So we'll call first on the list. And so after we have incremented this first element of the list, we want to attach it with construct to the rest of the list, but we want to also call our function recursively on the rest of the list so that those elements all get incremented as well. So we will call our incr list function recursively on the rest of the list. So now we'll close out our if statement, and we'll close out our lambda, and we'll close out our define. We can run this, and then we'll call our incr list function on a list, and we get back a list with all of the elements incremented. Of note, this is constructing a new list, right? We are calling cons. And so if I had defined L to be this list, and then I call incr list on L, L itself has not been modified. We have constructed a new list based on incrementing all of the elements in L. So now we also want to write a function to sum the elements of a list, and we'll also do that recursively. And again, it's recursive, it needs a base case. In our base case, we have an empty list, and the sum of an empty list is 0. And that will be the starting point that we can add all of the other elements to. So now in our recursive case, we want to add the first element in the list to the sum of the rest of the list. So we'll add two things. First of list, and then our recursive call to sum the rest of the list. Parentheses match. Let's close everything out. Run our definition. Sum of that list. 16 looks right to me. But some of the other built-in functions that operate on lists could have accomplished these same tasks. For example, we could have used a map, which applies the same operation to every element of a list and constructs a new list of the results. So, to do our list incrementing with a map, we could do map, and then the function that we want to map, and then the list that we want to map that function onto. So the function here, if we want to increment each element, this function will be applied to every element. So the function we could do would be lambda x plus x1. So this is a function. We haven't used a define, so we haven't given a name to this function. So right now it's just an anonymous function. But if we were to apply this function to an element x, we would get back x plus 1, and map will apply this function to every element of the list that we give it. If we were to run this on an empty list, we would just get back an empty list because there was nothing to apply the function to. But if we give it a list of numbers, then it will increment all of the numbers in that list. We could also have done the sum using built-in functions. This one's a bit more cumbersome, but it would use the foldL function. So foldL takes a function that applies to pairs of elements, and it will apply that function to each element of the list, combining it with a running total. So we give it a function, and that needs to be a lambda on 2 arguments, so lambda xy, and then what that lambda evaluates to. In this case, we want to add up the elements, so we can do plus x, y. And so then we need to give fold_L a starting value, right? So this would be the base case of our sum function, or the starting point as it works through the list. And then we give it the list of values we want to apply this to. And if we give the same list here, then fold_L will evaluate our function on 0 and 1, and then it will evaluate the function again on the result from 0 and 1, along with 3. And so since we are evaluating plus, we will initially evaluate 0 plus 1, and then we will evaluate that plus 3, and then that result plus 5, and so on. And so we get the same answer as our sum function. A concern with the recursive functions we've written so far is that they will take up a fair bit of memory to evaluate. We can't really run the factorial function on really large numbers, but if instead of our factorial function we had one to calculate triangular numbers, which is summing up the first n numbers, so this would just be replacing 1 with 0 and replacing times with plus. Now if we call triangle on 5, I didn't replace the recursive call, it's still calling factorial internally. Let's try that again. That looks better. So that's equal to n times n plus 1 over 2. And for this, I could call it on a very large value. And that works fine. But if I call it on too big of a value, the program runs out of memory. As the execution trace in the PDF shows, we are building up more and more values as we are calculating this on really big numbers. And so that is taking up a huge amount of memory. But the reason that this takes up a lot of memory is that we need to store the value of n to be added to the result of the triangle call. So if we instead define a version of the function that does these operations in the other order, first it adds n and then passes that into the recursive call, then we'll get an execution trace that doesn't grow linearly in the number of times that we've called the function, because the compiler is smart enough to clean up after all of the intermediate function calls if there's nothing pending within those function calls. So a way that we could make this more efficient would be to have triangle, instead of just taking n, it could take two arguments, n and a partial sum. And then we would, if we are adding in the n's as we go down the recursion, then we don't need to save the n's to be added in as we return back out of the recursions. And so we could replace this plus n with just a call to our recursive function where we are passing both n minus 1 and the partial sum plus n. And then when we get down to the bottom, we don't want to return 0. We want to return the partial sum that we've been adding each n to as we went down the recursion. So if we run that, and now we do triangle on 500, we needed to give it two arguments. So we'll give it an initial partial sum of 0. And that gives us back the same answer that we had when we called triangle on 500 before. But now if we call it on a really big number, and again, I need to give it a partial sum of 0, it has no trouble computing this really big value. I could even add in a few more zeros, and it takes some time because it is making a very, very large number of function calls, but we are not going to run out of memory here because we are not adding more and more memory for every recursive call. It's able to give us back the right answer at the end of all of those recursive calls. But this is, as we saw, clunky for the user. If the user wants to calculate a triangular number, they don't want to have to just pass in a 0 every time. So what we can do is instead have a helper function inside of triangle that makes it so that the user interface to triangle just takes the number n, and then the internal helper function will be tail recursive, taking n and the partial sum. So let's rename our triangle function to be try helper. And we'll also need to change the recursive call to be a call to try helper. And then we're going to tab all this in. And outside it, we will define triangle to be the lambda on one argument, which has inside of it a definition of a helper function. And then after we've defined the helper function, our triangle function can call the helper function, and it will pass in n and a partial sum of 0, so that the user doesn't have to worry about 0. It can just be called on n. So now we run these definitions, and we can now do triangle on 500, no partial sum required. So if we wanted to rewrite our sum function to use tail recursion, then we would want to add a helper function, and that'll be a lambda that takes the list and a partial sum. And we want to tab all this in. And our sum helper function needs to call itself recursively. And it needs to take in the rest of the list along with the partial sum added to the first of the list. So we want to do plus first with partial sum. And then we can get rid of that stuff. And so now we have sum helper is being called on the rest of the list and the sum of the first element and the partial sum. So then when we get down to the bottom, we want to return the partial sum. And then the sum function can call the sum helper on the list and a partial sum of 0. So now we can verify that sum still works correctly on a list. So we would be less likely to have the same running out of memory problem that we had with triangle, because here the linear amount of memory for all of the recursions is proportional to the length of the list. So we don't have this big O change in the amount of memory, but it still does take significantly more memory, and so it's nice to use tail recursion when we can. So that's it for the lab exercises. Hopefully you found that helpful. And if you have any questions on the lab assignment, definitely let me know on Slack or in office hours.